Okay, let's continue. Lab 21, which is about the cache structure. And we're going to analyze the iCache and data cache arrays and implement and test new cache configurations. We're going to implement different caches with different sizes, with different associativities, and we're going to compare their performance under different programs. As always, theoretical explanation and several exercises. No simulation here for this lab. So let's do the exercise, one of the exercises proposed in this lab. And we're providing for processors, well, in the theoretical part we explain how to implement new cache configurations, how to modify the size, how to modify the associativity. And for the workshop we already provide them the bit files for them. So we're providing 4 different bit files, one with a direct mapping and 2 kilobytes per way, another one with 4 kilobytes per way and also direct mapping, a two-way set associative cache with 1 kilobyte per way, so 2 kilobytes in total, and a two-way set associative cache with 2 kilobytes per way, so 4 kilobytes in total. And we are providing 3 programs. We're going to start with the original program or the baseline program, and we're going to execute it in different cache configurations to see the performance, and then we're going to apply 2 optimization, software optimizations in order to improve the performance of the baseline code. We'll start running the first program, which is a very simple program. It's programmed in assembly, but here, for simplicity, we include it in C language. So it's a program that reads 2 arrays, adds their elements, and stores it in a variable, accumulates it into C. The arrays are made of integers. They have 512 integers each. So for a one-way 2 kilobyte cache, each array would fit, would occupy the whole cache. Okay. So for each iteration, we're having 2 misses in this configuration because we're accessing A0. This will bring the first block, A0, A1, A1, A2, and A3. Remember that a block is made up of 16 bytes, so 4 integers fit into a block. So for the first iteration, we're bringing the first block for A, but then the first block of array B will replace the first block of array A, right? Because they are, well, they are aligned and they map to the same frame in the cache. Is that clear? Yeah. So in the second iteration, A1 will again miss, and B1 will miss because B1 was replaced by A1. So each component is replacing the other array, right? So we'll have misses, 2 misses per iteration in this case, for this cache, right? That's what we would expect, to have 2 misses per iteration. If we change the cache configuration to a two-way 1 kilobyte per way, in the 2 ways we have space for 1 block from A, 1 block from B. So we'll have a miss for A and B in the first iteration, but then the second, third, and fourth iterations will hit because they are not conflicting, colliding in the same, there's a space for both of them, right? And then in the fourth iteration, A4 will be a miss and B4 will be a miss because those integers are in different blocks, okay, in the second block. But then in the 5th, 6th, and 7th iteration, we'll see hits again, right? Finally, if we use a one-way 4 kilobyte data cache, in 4 kilobytes we have a space for both arrays. So again, we'll see the same behavior as with this configuration. we'll see two misses in the first iteration, but then 3 iterations with hits, right? We'll measure the performance with performance counters, and we'll see if what we expect is met in the experiment. So let's execute. Please do the activity with me. So we program the device, as always. We have to select the correct bit file. Be careful with that. There are 4 different bit files in lab 21. So let's start with the one-way 2 kilobyte configuration. Okay, one way, 2 kilobytes per way. So 2 kilobytes per way in one way, it's a 2 kilobyte cache, right? Data cache. This is always about the data cache. So let's program the board with this bit file. Remember to reset it and see if the program executes. And now we are going to load, and we're going to load the program, the baseline program. So labs part 4, no?
It's an FPL on the desktop.
Okay.
Left.
FPL. Okay. Labs part 4, lab 21, and you're going to use baseline. Okay, simulation sources baseline. So use that path. And start executing. And let me show you the program. You don't have to open it. I'll open it for you. So you can see here, I didn't explain these macros for initializing and reading the performance counters, but I told you that here we were programming the event that we were going to measure. And in the previous labs, we were measuring 0 and 1, which were cycles and instructions. Well, we've changed those values to 10 and 11. 10 is the number of accesses, 11 is the number of data cache accesses, and 11 data cache misses. Okay? So now we're measuring different events than before. We're having data cache accesses, data cache misses. Okay? So if you look at the 7-segment displays, you should observe 1024, which is 2 misses per iteration. Remember, we had 512 iterations. Okay? No, sorry, this was accesses. But if we change, no. Okay, the switch, my rightmost switch was set to 1. I've just set it to 0. 1025 accesses. That's because performance counters introduce a new access. Okay, but approximately 1024 accesses and 1024 misses. So 1 miss per access, right? As we expected. Okay? Now let's change the cache. Let's change the processor, actually. We're going to change the processor for a processor with 2 ways and 1 kilobyte per way. Note that the size of the cache is the same. It's a 2 kilobyte way. It's a 2 kilobyte data cache, but it's organized differently. It has 2 ways, not 1. Okay, in Vivado we select that bit file, 2 ways, 1 kilobyte per way, and we program the board, and we run the program again. Close OpenOCD and GDB and run again. And now, with the switch set to 0, we see the same amount of accesses, but with the switch set to 1, we see around 1/4 of the accesses. Okay, it's not exact, but we don't care about it's approximately 1/4 of the accesses. Okay, so as we expected, when we change from a 1-way to a 2-way cache for this program, misses are reduced from 1024 to around 250. Okay, 1/4 of the misses, right?
Can I just add one small
Yeah.
note? From a practical application point of view, this is far more useful when you're thinking in terms of Wi-Fi and packet routing. So 1/4 the cache misses is a lot when you have like gigabytes being transferred through memory and routed across. So MIPS is widely used in network routers, and these things are tweaked to improve performance. So if you have 2 ways, 1 kilobyte per way, small packets, it's good for it. But if you have jumbo packets, like very large packets, then the 1 way, 4 kilobyte way can be more useful. Just as from an application point of view, just to touch, yeah. Sorry.
No, thank you. So we have a better performance. We've reduced the misses a lot, obviously at a higher cost, because we need more logic for implementing this catch, and we'll have more energy. A 2-way catch is more energy consuming than a 1-way catch. Okay. Also here in this slide, you have the cycles and instructions for each case. We could measure them just by changing the events when configuring the performance counters, and you would obtain the same instructions but much less cycles, right? Obviously not 1/4 because there are other instructions, but you reduce the number of cycles in a good amount. Now, let's try a 4 kilobyte catch where we should observe something similar to the 2-way catch, because as we said, in a 4 kilobyte catch, there's a space for both arrays, so there won't be conflicts here. If we program the board with that bit file, which is called one-way 4 kilobytes per way, we program the board, we execute the same program, and switch equal to 0, 1025 accesses, switches equal to 1/4 of the misses, right? So, as we expected, we obtain a better performance again. Or again, at the cost of more area and more energy, obviously. Okay, a larger catch, more area, more energy. Now, the second part of this exercise is to show different software optimizations. Here we will only show some of them, but there are others in the documentation, such as blocking, loop interchange, and others. You may be familiar with those. Here we only show 2 simple ones, array enlargement and array merging. Array enlargement keeps the code exactly the same, but it increases a bit the size of this array. That way we are not having B array perfectly aligned with array A. So this will move the blocks of B mapping a bit, and blocks of A and blocks of B won't conflict in the catch. You see that? Yes? So when we now are in iteration 0, A0 goes to a different frame than B0. So they are not replacing each other, and will improve performance by reducing the number of misses, right? So let's try this. This program is also available in the workshop contents. It's called Simulation Sources Array Enlargement. So let's try again the configuration with the smallest catch size, which was 1-way 2 kilobytes, right? We go back to the smallest catch. We program the board. If we execute the baseline program, remember that we have the same number of misses as accesses, okay, 1025, 1024, but if now we execute the optimized code, which is in folder array, what was the name? Array enlargement, yes. You will see how number of accesses is the same, but number of misses has reduced to 1/4 of the misses, right? With this small trick of moving a bit the array so that its blocks don't conflict with the blocks in the A array. And this is at no cost. It's a software optimization. So the catch needs not to be changed. Okay? And if we measure a number of cycles, we'd see how they also reduce a lot against the baseline code. Right? You can do that on your own by just changing the events from 10 and 11 to 0 and 1. Okay? And finally, another technique that is shown, I told you there are several, we're showing here 2 of them. This is array merging, which is a similar concept. In this case, we make more changes to the code. We organize the arrays in a structure, so they are interleaved in memory. We have a component of A, a component of B, and then the second component of A, and the second component of B. So again, we won't have conflicts there. We are bringing a block that contains the first 2 components of A, the first 2 components of B. So in the first iteration, we will have 1 miss and 1 hit. In the second iteration, we'll have 2 hits. In the third iteration, we miss again for A, but we hit for B, and so forth. So 1/4 of the misses again, as with the previous technique. Let's try it. We can try it by executing. Now the name of this program is array merging. And let me show you, number of accesses and number of misses is reduced to 1/4 of the misses, around 1/4, right? Some other applications are shown, such as matrix multiplication, and blocking is applied in that case. So the idea is to show different software optimizations, also different hardware optimizations by reconfiguring the catch and generating new processors, and so that the student can understand the difference between all of them and test them with the performance counters. Yes?
The enlargement, the array enlargement is something that I did not understand very well. So you add 4 elements in the definition.
So maybe I can show you here. So you have array A, array B.
Yeah.
They are stored in memory, so this is component 0, 1, 2, and 3. Until 511, and then component 0 of array B, given the catch size is prepared so that this happens, maps to the same frame in the catch. So in the catch, when you access A0 in the first iteration, you are bringing A0 to A3. And then when you access B0, the block where B0 is in maps to the same frame in catch. So it will replace A0 to A3 and store B0 to B3. But then in the second iteration, you want to access A1. But it was replaced by B0 to B3. Okay, so each block replaces the other array, so you have all misses. What we did is we extended A. So let's say that here you have A with fictitious number, with empty values, but just to make B start a bit later, right? So B will, in fact, start at the same position as A4. So this block this first block of A will not collide with the first block of B. They can be at the same time in the catch because B0 to B3 is here. They don't collide. And then A4 to A7 goes here. It replaces this block, but we don't need this block anymore, and we need B4 to B7, which is in a different frame again. You see? Okay. Okay, let's go into the catch controller. This is divided in 3 labs, well, or 4 labs, because lab 22 has 2 documents associated with it. It's quite long, so it would be as if we had 4 different labs for analyzing the catch controller. Okay, it goes complexity increases. Lab 22 explains how hit and miss are managed in the catch controller. Then Lab 23 explains the catch content management policies that are implemented in MicroActive. And finally, Lab 24 explains how the store buffer and fill buffer work. This is the first time we're going to execute and try to analyze store instructions. So far, as for memory instructions, we've only analyzed load instructions, which are far more simple. Store instructions are more complex because they go through a store buffer. They will be written to the data catch later, as we will see in Lab 24. Okay, so this is the first time we will introduce store instructions. But let's start with Lab 22, which explains hit and miss management. We're not going to do any more hands-on activities. This is theoretical. We haven't included those activities in the workshop, but there are many other exercises around these labs. So analyze how iCatch and data catch hits and misses are handled by the controller. And here is the picture, similar to the pictures we used in the instructions part, that explains how we handle a hit. Well, how we determine if we are having a hit or a miss. Okay? So this is we're doing it for the iCatch, and we're asking the student to do the same for the data catch. It's very similar. Okay? It's very similar. There are some small differences, but it's very similar. So for the instruction catch, we have to, at the pre-I stage, we compute the next PC. Okay? And the next PC is provided through these registers to the next stage, which is the one which evaluates if we have a hit or a miss, and in case of a hit, we provide the instruction. In case of a miss, we request it. So the PC, which is a virtual address, is used to index the iCatch. So catches in MicroActive are virtual indexed, physically tagged. Are you familiar with that concept? They are virtual indexed because they are indexed by the virtual address, by the PC, but they are physically tagged because the tags are compared against a physical address, not a virtual address. The benefit of this approach is that the virtual address is ready at the beginning of the cycle. You don't have to translate it. So you can start the catch access at the beginning of the cycle. And at the same time, in parallel, you perform the address translation. There is a module, memory management unit in MicroActive that you could analyze. We don't do that in these labs, but you could analyze. You have the software. And it is used for translating from a virtual address to a physical address. It has a TLB. Okay? You could check that. It translates from the virtual address to the physical address. At the same time, we are obtaining the information from the catch. Okay? The catch is outside the core. Sometime later, we obtain the instruction or instructions. In this case, this picture is for a two-way catch. So we obtain 2 instructions and 2 tags. Okay? What we do then is we compare the 2 tags against the physical address because it's physically tagged. Okay? So we compare the 2 tags with the physical address. in this comparator. This will determine if we have a hit or a miss. If we have a hit, we have to select the correct way, or the way that hit. Can be this one or this one because it's two-way. So we select the way that hits and we provide the instruction to the instruction register for execution in the next cycle. Okay? That for a hit. If we have a miss, we stall the pipeline. We cannot provide the instruction in one cycle because we have to request it to memory. And some cycles later, we'll have it ready. But for that, we have to stall the pipeline. So we inform the control unit that a miss has been detected. The control unit, as we will see later, requests that block to main memory, and sometime later, some cycles later, we will receive the block back and will be able to execute the instruction. Okay? But now we're with the hit. So let's assume that we detect a hit, we select the correct instruction, and we provide it to the E stage in just one cycle. This is how the hit or the miss are detected. Any question about this diagram? We're going to see a simulation now. So please open the slides in your screen. This is the program we're going to evaluate. We want to force a hit. How can we force a hit in the instruction catch? Very simple. We create a loop. In the first iteration, instructions are not in the instruction catch, so they will miss. But then from the second iteration on, they will be in the instruction catch, so we will detect hits. Okay? So we'll analyze the simulation of the second iteration or bigger, not the first iteration. And here are the results for this program. Okay? So here, this is the pre-I stage, and E stage. So in the pre-I stage, the next PC that we'll fetch is the PC for the add instruction at this moment. Okay? 20C. That's what we have there. In the I stage, we access the catch based on this PC. It was virtually indexed, so we don't need to translate this into a physical address. We directly access the catch. And this is what we obtain. Remember, we have two ways, so we obtain two instructions. One is the instruction that we are requesting because we have a hit. The instruction is in the I catch. It was brought to the I catch in the first iteration, right? We have the instruction, you can read there, 018B, 018B, 6820, 6820, right? That's the instruction we're requesting. And the other thing has not been initialized. Okay, we've not used the other way yet. Okay, so it's empty. We detect a hit. Look, this is the hit signal. This is one when we detect a hit in the I catch. So in this cycle, we detect a hit. We found the instruction we are requesting, right? We detect a hit. We select the correct way, not the first one, but the second, not way 1, but way 0. We select it, and we pass that instruction to the next stage without stalling the pipeline, so that it can be executed. Right? You understand? Yes? Any question about the catch hit? Well, as I told you, there are some exercises that we haven't included here because of the time, but that you can look at them. Now, this is more complex. How do we handle a miss? And in fact, it's simplified here. You could even complicate it more, as you will see. When there is a miss, we have to do several things. First, we have to stall the pipeline. We have to stop execution because we need a data that, or an instruction in this case, that we don't have. We have to request it to memory. So we have to stop execution for some cycles, the miss penalty. We have to request the block to main memory, not only the instruction that we want, but also the whole block for exploiting spatial locality. So we have to request the miss block to main memory. But that's not all. We also have to select a catch block to replace. You remember that, right? When you want to insert a new block, maybe you need to replace another. There's a catch replacement policy there that we'll see in a later lab that determines which block are we going to replace with a new block in the catch. And also, probably we need to copy or to update the block to main memory in case it's dirty. If we are using a write-back policy, the block may have been written and not updated in main memory. So when we evict it from the catch, we have to update it to main memory, right? So all these things we have to do when we detect a data catch miss. And we want to resume execution as soon as possible, so that performance is not penalized or is penalized as little as possible, right? So MicroActive implements a policy called critical word first, which requests to main memory, as we will see, the word that is requested within the block. First, the word that is requested. You'll see later in a simulation. For this part, we use always the same program. Let me highlight something here. We have a load instruction here that we force to miss in every iteration. We force a catch miss, a data catch miss in every iteration for this instruction, right? That way we can observe what happens there. So let's go. We said we need to do three main things. Let's go through them now. First thing, we have to stall the pipeline, right? We have to stall the pipeline for some cycles. The miss penalty, that's called the miss penalty, okay? The number of cycles that we have to stall due to a miss. And you have a simulation of what happens, and you can see many things here, but let me highlight here that you can see that for 4 cycles, many things in the pipeline do not change, right? Stay the same, because we have stopped it, we have stalled it, okay? We are waiting for the block to come back so that we can continue, right? So for a number of cycles equal to 4 here, for 4 cycles, we have to stall the pipeline, and you can see it very clearly in this simulation. Now, second thing, we have to request the block to main memory. This is simplified. We're not going to evict blocks or to replace blocks in this simulation for simplifying it. We just want to see how we request the block to main memory. I think that's quite interesting. You could also have interest in doing more complex things. You can just change the program and observe them in simulation. You can ask your students to do that. But this is a simple example that shows how we request the missed instruction. And here is the logic that the software includes for doing that. Okay? Let me show you that logic with an example. I think you will understand it better with the example. Please open that slide in your screens so that you can observe the details. So what we're, okay, as Suber said at the beginning, the bus we're using has 32 bits, okay? The data, it has several buses. The red data bus has 32 bits. Also the address bus has 32 bits. So in a 32 bits, we only can fit one word, one integer. If we are requesting a whole block, when we miss, we need several cycles for obtaining the whole block, okay? Several sequential cycles. Specifically 4 cycles for obtaining the 4 words that make up the block. So this logic is generating 4 pulses, 4 consecutive pulses. In each of them, we are requesting one word within the block, right? So you can see in the simulation that we have the 4 consecutive pulses when the miss is, well, here you have the miss signal and a miss is detected. This is 1 for 4 cycles. We have detected a miss. So this logic generates 4 consecutive pulses, and during those pulses, it's requesting the 4 words that make up the block, right? It's 2 for C, 2 for, no, what's the number? 2 for, no, yeah, sorry, 284, 288, 28C, and 280, right? Those are the 4 addresses for the 4 words composing the block. Okay? And one cycle later, because this memory answers in just one cycle, that's a bit idealized. That's not what would happen in a real memory. Okay. So we are obtaining the data that makes up the block, right? So these are the 4 words that make up the block that we missed before. Note that the block is not stored directly in the data cache, but it's temporarily stored in a field buffer. It will eventually be copied to the data cache, but not yet. So I think this is very interesting because the student can see how the block has to be requested in several cycles. The processor has to wait until the requested word comes back from main memory, and then, only then, it can continue execution. Okay, any question? Now, finally, as I told you, the processor implements the critical word first policy, meaning that we are not requesting the first word within the block, but the word that the instruction requested, so that we can restart execution as soon as possible. Well, in the previous simulation, you could observe that we are requesting the second word within the block, and that's the first word that is requested. This is 284, 288, 28C, and 280. This would be the first word within the block, but this is the word that we requested. That's why we requested firstly to main memory, so that we'll receive it back from main memory, the first one, and then we can resume execution very soon. In fact, when we resume execution, the whole block has not been transferred yet from main memory. It's still being transferred. At the same time, we are resuming execution. You can see that in the next simulation. Here, we are resuming execution here, and we are still receiving through the bus some words that belong to the block. That's okay, we can do that, because the word we are requesting is this one. That's the critical word first policy, and it's used in MicroActive for performance. Okay? As you can see, complexity is increasing now. These are not labs for first year students, they can be more for last year students or even for master students. But they are nice, I think. Okay, any question about hit and miss management? Yes?
So how these caches are implemented in FPGA? Is it a block RAM?
Block RAM, yeah, and the memory too. In fact, memory too, yeah.
So the block RAM usually itself as a block. You give address, it gives you the data in the next cycle.
Yeah, that's the catch.
The
block RAM? Yeah, the block RAM can give you the data in one cycle, but you are using it as if it was a main memory, so you have to request through the bus interface unit, and you have some delays for that.
I see in the cache hits case, you give the address and the data comes in the same cycle. Looks like
no, in the next cycle, right?
So you're saying the address feeds to the memory in the prefetch, pre-I stage. Right, we can take it offline.
Okay. More questions about that? Okay. What time is it? Yeah, I think I'll not go into many details now. I'll try to give you an idea of what these labs are about, because it's too dense. We've seen too many things, and I don't know. You looked very tired, so let's try to summarize a bit. And still, you have to explain SOC.
I have the section.
So, okay, cache content management. The goal is to analyze the different policies available in MicroActive for managing the cache contents. MicroActive implements a true least recently used replacement policy. You must be familiar with this policy because it's used in almost all processors nowadays. Although there are many proposals for improving it, they are not used in commercial processors. They are just used in research. But nobody has been able to improve performance of least recently used, or not so much that you want to use it in a real processor. So microactive uses a true LRU implementation. Some other processors use pseudo LRU implementations, simplified LRU for reducing the cost, but microactive uses a true LRU. I'm not going in detail of the algorithm. You have all the details in the documentation. You can look at that. It uses 6 bits per set. Sorry. And one of the exercises that we ask the students for here is to implement a new replacement policy. And here we propose to implement a first in, first out policy, used in some cases, some specific cases, and compare it again with the performance counters with the true LRU that microactive implements. This is not an exercise for a single lab. This is more like a final degree project or something like that. Okay, it's quite a long exercise. The students will need some time for understanding this part of the catch controller. It's not easy for doing it in one session. Okay. Also, and this is more doable, we will try different write and allocation policies. Those are configurable in software. When you boot, you can configure the policy to use. Microactive allows you to use a write-through, write-no allocate, a write-through, write allocate, and finally a write-back, write allocate policy. Right? 3 different policies that you can test over different programs that we provide, example programs. Okay? Lab 24. It analyzes the store buffer and the fill buffer. The store buffer is used for holding the data to write to the data cache by a store. So the store modifies the data, so it doesn't write directly to the data cache, but it writes through a store buffer. Also, when you bring a block from main memory, you don't write it directly to the data cache, but to a fill buffer that eventually will write it to the data cache. Okay? Well, this is the diagram for the fill buffer and the store buffer. Again, not going into details. Look that they write to the data cache. This is the data cache. This is the store buffer, and this is the fill buffer. They can even communicate among them. In some cases, that's useful. And then we analyze a simulation here. The simulation is quite interesting because, can you open please in your screens? Let me just highlight a very small thing. So what we are forcing here is write miss. We are writing data, but also we are missing in the cache. So the process is, we miss, so we have to bring the whole block, and then we change one word within that block. Right? The store will change one word within that block. How is it handled in the cache controller? Well, the most efficient way of handling it is merging everything in the fill buffer. And you can see that here, in these 4 signals. This is the fill buffer, okay? So as you can see, we are writing a 4, a 6, and a 7. And here, well, the thing is that we are writing directly to the fill buffer. So what we will write to the data cache is not the original block, but the block with the word modified by the store. We are merging everything in the fill buffer, the block that we bring from the memory, and also the word modified by the store, and then we are updating the cache with the new block already updated with the store data. Is that clear? Yes? And that's the most efficient way to do that. Okay? And that's shown in this simulation. where we can also see the data cache and how the field buffer is finally written to the data cache, and also to the tag array and to the way select array. Well, as exercises of this part, we propose different sequences of store and loads with specific characteristics, and then we ask the student to simulate on their own and to analyze the results, right? Complex sequences where specific things happen so that they can see how the catch controller manages those situations. Finally, Lab 25. We are going to implement a scratch pad in microactive. That's very nice, but again, quite a long project. We give instructions about how to implement a scratch pad. The interface is ready, but you have to implement the real scratch pad and enable it. We're doing an instruction scratch pad. The scratch pad is mapped to this region, while the memory and the caches are mapped to a different region. As you know, the scratch pad is software managed, not hardware managed, so the programmer must initialize it and handle it and access it. And the exercise will compare the execution of an algorithm from the instruction cache and from the scratch pad, from the new scratch pad, right? So the algorithm, well, this is impossible that you can read it, but that's not the objective. I just wanted to show you that we're going to measure with the performance counters the execution of this algorithm, which is extracted from, again, from Harris and Harris' book. It's another exercise that they propose there. So we implement that algorithm, or we provide it to the student. They implement the scratch pad, and then they execute this algorithm from the instruction cache and from the scratch pad by using this code. This code jumps to the address mapped to the scratch pad. So it will read the code from the scratch pad. The scratch pad won't miss. It will access the instructions in one cycle, all of them. We have to initialize the scratch pad. We first initialize the scratch pad, but then when we access that code, we never miss. Okay? So performance, in this case, will be much better, and you can obtain results like this, where the CPI, when you execute the algorithm from the iCatch, is almost 2, whereas when you execute it from the scratch pad RAM, the same algorithm, exactly the same, it is reduced to almost 1/2 of the CPI. So much better performance in this case. Any question? Okay, if you are interested in these last labs, you have all the documentation available in the whole package. You can look at it. The solutions are there, so you can look at them on your own.
Okay. All right. So we started off with the MIPS microactive core. We wired up some clock reset, AHB peripherals. We looked at the input-output, 7-segment LEDs, switches, interrupts, how we can work with that. Then we moved very much deep inside the core, performance counters, caches, cache misses, how the add instruction flows through the pipeline. Let's try to step outside the core now. Like now that we are not going to look inside the core, we're going to try and step outside the core and how we can use MIPS. So as far as MIPS is concerned, we're going to use MIPS as one block. We're going to think of it as a processor and how we can use the MIPS processor in products. So think of it from a software perspective. Just simple while loops, it's all fine for small microcontrollers. But if you want to run, for example, what's running on this camera here, it's a lot of processes are running, there's lots of video streams coming through, lots of configuration, there's a display handling as well. So there's a complete environment, a multiprocessor environment here. So you start going into the field of operating systems. Okay, so we want to use the MIPS. The MIPS is a microprocessor, it's a soft processor, but the hardware can run an operating system as well. So we want to go beyond simple C programs, which have, we want something which has many threads, processes, it manages the memory, and we use a simple we use shared standard libraries, run Linux on the on MIPSfpga, basically. So this is the main goal that started the whole MIPSfpga SoC project, as to how we can run Linux on this platform itself. So as I said, we're not going to look inside the core now, we're going to focus on outside the core. Okay, so up until now, we have looked at the Nexus 4 DDR board as the FPGA board. We have the MIPS RTL and the AHB Lite RTL, it's the Verilog, and we have the LED Blink Verilog module and some C code around it as well. Now think of both of these together, the Nexus 4 DDR and the FPGA software implementation, as the hardware. Just think of this as the hardware itself. The operating system basically sits on top of this hardware. It manages the hardware, all the different features it provides, and then applications basically run on top of the operating system. This is a layered hierarchical system where complex products end up being produced. That's how it works. And then the user, so if you use a monitor, as like a keyboard or a monitor, so you're on the user side, you converse with the applications converse with the operating system, and the operating system handles the hardware. Okay, so within the operating system, there's a concept, a further subdivision of kernel space and user space. So it's more of the kernel space touches the hardware specific parts, the user space looks at the application side of things. Okay, so a few examples. You have a Samsung phone, HTC, LG, whatever. You have the Android kernel. That's the kernel space part. See, this shaded area is like specific, like it's a common overlapping zone. Then you have the Android user space part. What you see on your phone, that would be the Android user space part. Behind the scenes, while it's powering up and it's handling that would be the kernel space part. And then you run apps like the phone call, Angry Birds, WhatsApp, or some other apps like that. Okay. So similarly, Linux runs on hardware, a hardware platform. You have the Linux kernel, and then you have the Linux user space, and you go up to applications like Vivado, Firefox, or something like that. Okay. So we call this boundary between hardware and Linux kernel as architecture specific. So you can run Linux on your laptop, on your server, these are Intel processors. You can run Linux on your Wi-Fi router, that's MIPS processor. On your phone, it's ARM processors. So this is an ARC-specific layer, okay? The boundary between Linux kernel and user space, it's another standard. It's a various number of syscalls, and there's a hierarchy here. And the boundary between user space and applications, various SDKs that handle this, okay? This is how software overall builds up. So just to recap, we have the operating system, we have the Linux kernel, and we have build root user space. So basically, the Linux kernel is a common component. You'd be surprised to know the Linux kernel in servers, in the phone, in the Wi-Fi router, the code base is the same. It's the architecture specific bits and the configuration that changes, but the general code base is the same. The user space part, completely different. Ubuntu, completely different. Android user space, completely different. Wi-Fi router user space, completely different. Now, build root is a small, tiny, embedded user space, which we use for our MIPSfpga SoC platform. Okay. So now, before we go into trying to build a platform that can run Linux, we need to know what are the hardware requirements that can run Linux, because Linux is a complex piece of software basically, and it has a lot of requirements on the hardware to provide features. So the minimum requirements are a CPU with a memory management unit. So we haven't touched memory management unit in terms of virtual memory and physical memory as such, but the microactive does provide a memory management unit. Okay, well, we need a timer. We haven't touched timer as such, but we need a clock source, because if you're pressing Alt-Tab and switching between processes, you'd want your music to keep running in the background. So there has to be a sense of time in the whole system, and Linux expects a sense of time in the whole system platform. there needs to be an interrupt controller. As I said, when you switch processes, you switch between your music player and your Firefox tab, you need interrupts to go from keyboard, and you need your the rest of your applications to keep running in the background. Okay, you need DDR memory. Okay, so up until now we've been using 1 kilobyte of scratch RAM. It's SRAM on the FPGA, 256 kilobytes of scratch RAM still on the FPGA. That's too less for Linux. You really need something like 4 megabytes on the very minimum side, ideally 16, 64, and you can go 64 gigabytes if you want. So now the fifth part, UART. Okay, so up until now we've been loading stuff on using Bus Blaster, but we've been interacting with our applications with switches and LEDs. That's a bit hard. So you need actual, like, you want to send commands to your process and go back. You need an interactive console session. It's basically like the command prompt window you open on your Windows machine. It's like you want that level of access to go through back and forth between your embedded Linux machine. So the sixth thing, of course, we need EJTAG because that's how we're going to load the entire Linux binary. All right. So the bonus peripherals, so the Nexus 4 DDR board, yeah, just a word of caution, this starts getting very specific to the Nexus 4 DDR board, because when you start building this platform, you start using bits which are provided far too much by the hardware. Bonus peripherals, so we have an I2C controller and an I2C temperature sensor on the bottom right of the Nexus 4 DDR board. So that, and we also have Ethernet, an Ethernet port on the Nexus 4 DDR controller. So yeah, if you have all of these, then you get a good platform. It can run Linux. You can start working more. Okay, so in terms of SoC design, as I mentioned, think of this as in blocks. Okay, at a top level layer, not low level cache miss hit. No, just as a top level, think of MIPS as a block. What are the other bits in our SoC block that we need to run Linux on our final platform? You have boot ROM. You start off with boot ROM at 1FC. You have DDR. DDR for MIPS, it should be at 0x0. Ideally, it's just the easiest memory map to have 128 megabytes of DDR at 0x0. Then you have a GPIO controller. You still want switches and LEDs. You have serial, interrupt, I2C controller, Ethernet controller. These are all different blocks, Verilog modules, if you call them, like various Verilog modules. Then you have a MIPS module on the left. I'm sorry if you can't see. Then you have a MIPS here. Then you have an interconnect to communicate between all. This is what was the EHB bus section. So here you have an interconnect which communicates with all these blocks. The MIPS is the master here. Okay, and just to elaborate, the Linux kernel from the software perspective sits on top here. It communicates with the MIPS and handles all the hardware bits, and the Linux user space build root sits at a layer above here, and then you start running your own applications that you want. All right. So just to recapture again, as a comparison between the current MIPS RTL, simple AHB like Verilog, our own simple C applications here. In terms of MIPSfpga SoC, you have your MIPS core RTL, yes, but your AHB Lite is completely different. You have your SoC design, then you have your Linux kernel software. Here, the hardware boundaries. You have your kernel software, then you have your Linux user space, then you go into applications. All right. So this is what it starts looking like in Vivado. Okay, so I'm gonna try. How much time do we have? 17. That's a lot. Okay, so I'm gonna try. So we don't use handwritten Verilog anymore for this level of complexity. We start using, let me just open something 1 second.
Is there some information on how to extend the peripherals? For example, the SD card, is that provided, is that supported under
so
DDR, the Nexus 4 DDR?
Yes. So SD card is the most common question everybody asks because they can see it. The problem with SD card is the specification is a closed source thing. You have to pay a license fee to start looking at SD cards in terms of software. The hardware is there. We can't like give it or anything. We don't even have, because we wanted to make
MIPSfpga SOC as openly accessible as possible. So we use freely available Xilinx IP blocks. Xilinx don't provide an IP block for SD cards as an SD card controller. You're gonna have to purchase one.
I mean, if you would like to want to add an
yes, you can.
device that is available in Xilinx,
yes.
for example, motherboard.
Yeah, you can. You can. Let me see. Where? Project Linux. Okay. Oops. Okay. One other side note. This project is specific to Vivado 2014.4 at the moment. Yeah, it's opening. This one. 1 second. So it's gonna open in read only. Yeah, I'll open Vivado 2014.4. As I mentioned, it starts getting very specific to the hardware, and because we use Xilinx IP blocks, it starts getting specific to the Vivado version as well. Updates, while possible, failed to install all user apps. That's fine. 2016. Did it crash? Too many Vivados. So let's just. So the first thing was to package the MIPS core RTL into a piece of a block, which Vivado's GUI tool called IP block design, IP manager or something like that, that it can use. So after packaging the MIPS as a block, we have to basically tell Vivado that this is an AHB bus, this is a clock, this is some signal. Then you can start using its block design tool. So you might have, if you've used, what's it called, QSys in Altera's tools and in Vivado's tools, the microblaze examples, this is on the similar side. So if you do, it's been a long day, I think. Yeah, create a block design. Okay, so right click, add IP and type MIPS. So you basically add the MIPS IP core as a block. So if we want to start, so we have an AHB light bus. Now Xilinx's IP peripherals are all AXI bus. So we do have an AXI to AHB light to AXI bridge IP block. This is provided by Xilinx themselves. It's all part of the same webpack. So academics do get access to this. So you click and connect the interface, and it wires up all the signals by itself behind the scenes. Okay. The next step, we had an interconnect. What's it called? AXI interconnect. So then this will allow us to connect multiple peripherals because we had GPIO, I2C, UART. So you can connect multiple peripherals from here. So now once this is done, you can basically start adding block RAM, AXI, AXI. So once you have a bridge to AXI, you can basically use all of Xilinx's AXI peripherals or any other peripheral if you have. It's like it's a widely known standard. So we add a block RAM on this side, connect it. What else? GPIO. Okay, GPIO controller. I wanted to show you one other thing. Okay, so we haven't wired the clocks, we haven't wired the reset. And how do we know the address map? See this tab here. So it understands that the MIPS is an AHB bus master, and that it understands it's a 32-bit address bus, 4 gigabytes, and then it has 2 unmapped slaves. So here you start auto-assign addresses, and it tries to auto-assign, okay, I'll call a block RAM controller 0xC000, but I don't like that because MIPS core comes out of reset at 1FC0. So I'll just change the address editor here. And similarly, GPIO MIPS SOCs do have a bit of a convention as to where we put our input-output blocks. So we just put it at 1060. So if we want, as you asked a while ago, if you want to add our own peripheral, you basically double-click the interconnect and add number of master just add more interfaces here. Once you have more interfaces here, you can basically add any more IP blocks. So if I right-click, add I2C, an AXI I2C bus master, not yet installed. Yeah. Wow. So we'll choose something else. Ethernet Lite. Okay. So I'll add Ethernet Lite as a third connection, as a third IP block. In the address editor, it will appear as an unmapped slave. So I'll just map it at whatever physical address I want. So this is how we basically build up our SoC design. Now imagine those cooking videos that here's the cake that I prepared earlier. And I'll show you the complete design. Oops, no, not that one. Yeah. So if you add all the blocks in this IP manager tool, IP integrator it's called, then you get something that's a bit more complicated. It's a bit big. I think I can remove various signals. 1 second, let me search. Yeah. So this is slightly more visible. So it only shows the bus connections. If you can see, it's the MIPS microactive, HB Lite bridge, interconnect, Ethernet Lite. This is the physical signal on the Nexus 4 DDR port after the PHY. GPIO, block RAM controller, interrupt controller, UART 16550, and another custom AXI GPIO. So when you asked a question that can we add our own, so there is one exercise which is basically a wrapper kind of simple AXI peripheral. If somebody wants to start, this would be the starting point.
GPIO, but I mean
memory mapped I/O, anything.
To another port, for example.
Yes.
There's another Ethernet controller. For example, if you would,
just right-click, add an interface, and connect it with an AXI bus.
And how does Linux know then that?
You write the Linux driver. Yeah. So these ones, the kernel drivers exist, and we've done quite a bit of work. So if you have your own custom peripheral, you need your own custom software anyways. So it's the whole stack from Verilog to Linux. You can see all the source in the whole process here. Okay, so if I enable all the other interfaces again, so basically all these wires, they're like clocks, reset, lots of different things, so interrupt controller wiring. The first step documentation, I basically wrote all the documentation to connect each signal step by step, explaining how it's done and why it's done. So it steps through basically from nothing, from just the RTL, how to package it, and then how to wire every single bit and build it all together. And there are a few structured, like similar to the getting started guide in labs. There are, I think, 5 labs for RTL design to build up this. And then we move to 5 labs for the software. So there's a lab to port the Linux kernel onto this new platform, because this is a new platform. The kernel won't have any idea about the platform. So you have to add the device tree support to the Linux kernel as to how it knows. And then a lab on build root, and then a user space application as well on how we can start using it. Okay, so let me just memory map here. Okay, yeah, I'll try and demo this. We have OpenOCD, GDB, no. So it doesn't use the same load MIPSfpga batch script, and there's a subtle reason for that. Let me start loading the bit stream and I'll explain. So the Linux kernel, it expects that whatever platform it gets, the cache will be initialized, and the hardware will be somewhat initialized. This is basically the job of what we call the bootloader. It's also called, like, there's a popular one called U-boot. So we use the bootloader basically takes the hardware from basic reset to a sufficient state where then Linux can take over. Okay, so if it's a multi-core system, not in this case, the bootloader runs on the first core, makes sure the other cores are all silently idling, and then hands off control to the Linux kernel, and the Linux kernel can then start proceeding with the rest of it. So in our case, the boot code is running on the, oops, no, I pressed the wrong button. It reprogrammed itself. Okay, so now that I've flashed the bit stream for all this SoC design, we also pre-initialize the memory file. Now, pre-initializing the memory file with a bit of basic boot ROM code, which basically just loops through, enables the cache, and outputs MIPSfpga on the UART, actually. So we can look at it outputting, if it works, 1 second. Yeah, so this is the boot code, just basic C code. It initializes the cache, it outputs these characters on the TX and RX stream. If you look at the camera here, 1 second, oops, not this one. Yeah, this one. See this LED in this corner? It's a TX RX LED of the UART wire. So it's basically communicating. Yeah, I forgot to mention this power cable. It also multiplexes with the UART. So that's how the UART is coming onto the laptop, basically. Okay. So at the moment, Linux is not running on the platform. We just have the RTL, the same program memory. It was already pre-initialized with a loop which initializes the AXI UART 16550, which is a standard IP block. It initialized it and it outputs the character stream MIPSfpga on that. So after this, we can load. Let me see if OpenOCD is broken. Okay, 1 second. So in this case, you have to run OpenOCD yourself. Because the load MIPSfpga bat script basically resets the core and then loads the program. We can't have it do that. We want our boot ROM to initialize the cache and keep the platform in a ready state, and then load the kernel and jump into it. Where's the OpenOCD Nexus for bat? So this time I've just run OpenOCD. I haven't run GDB yet. So now I'm going to manually run GDB. Nope. Desktop FPL. These files are in your workshop folder, by the way. And we have what's called a starter tutorial that walks you through this entire process. And then we have other complex step-by-step building up the RTL design. I'll give an overview in a while, 1 second. -GDB-X. Okay, so now we can stop it. Okay, paused, load VM Linux. This will take a while. It's a large binary. It has the kernel, it has build root user space, and it should hopefully work. This is prone to error because there's a lot of manual steps in getting OpenOCD running. Okay, so what do we have up until now? We have our SoC design. That's the Verilog SoC design combined with the Nexus 4 DDR. We get a resulting platform which can run Linux. Okay, and we have the Linux kernel. Now we're loading the Linux kernel over JTAG. It's taking a while. And we also have communication through the serial port. At the moment, it's just one directional communication. But after Linux is loaded, we can hopefully, let's see, this putty here, continue. So this is the Linux boot ROM at the start I'm supposed to ask who has used Linux. So right now I'll ask, has anybody used Linux? And then embedded Linux as well. So you might be familiar that this is the early boot log that you see. So it's Linux version 4.1 like compiled, and it's just when I come here. Can everybody see? It's too small. Can I change this? Font colors. Okay. I don't know where the font is for this. Okay, so we can type commands in through the serial port, and it's basically a tiny Linux running on the resulting platform. So if you want to see interrupts, cat/proc/interrupts is a file. We read it cat/proc/cpu info, and we read information about the MIPSfpga platform. Now I remember I mentioned the I2C controller. There's a temperature sensor on the board. So the Linux kernel does have a driver to access the hardware IP block through AXI. So if I do cat/sys class hwmon 0 device temp1 input. So the kernel abstracts the temperature sensor value in a file, and if I read that file, I'll get a value from there. If I press my hand, where's the temperature sensor? It's here. Yeah. So at the moment it reads as 28555. It's not calibrated in terms of degrees or anything. And after I press my finger, it's 28320. Yeah, it just keeps reading the temperature. If you hold a torch next to it, it heats up and the value rises. Okay. So just to take a step back, so we started at the very beginning of the workshop with just the MIPS core RTL. Wire up the clock, wire the reset, HB light peripherals and stuff like that. We started with we went into interrupts, some LEDs, then we went into the core inside, caches, and how all this working. Then we took a step back, went to SOC. So you go from a very base register ALU base layer, build it up, and you can run a whole complex piece of software, embedded Linux on top of that. In this particular case, you can follow the entire source from scratch to the very end. As to you can look at the entire source, how it all built up to produce this. Now it might look simple, but lots of Wi-Fi routers on the inside just look like this when you access the terminal access. Okay. Now I hope I haven't bored you a lot with our SOC. Just to wrap up, yeah, we use Xilinx's IP blocks. They're the Linux kernel software port is of course open source. The kernel's open source. The Xilinx IP blocks, they're all part of the same license. Build root is also open source and available. The MIPS block in the whole SOC design was by imagination. The AXI IP blocks were from Xilinx. There is a custom basic GPIO block. That's just as a shim wrapper kind of thing. If somebody wants to start their own AXI peripheral, this is a starting point there. And there's also a kernel driver starting point for this as well. So you have some memory map access from user space to this. It's called user space IO, and there's a whole subsystem for that. And then we have structured tutorials. And the teaching package itself has a lot of tutorials that stepwise build up this whole SOC package. Okay, so just to conclude, on our SOC side, the complete stack from Verilog to Linux is openly visible and at an industrial level. This isn't like a small written application. The same microactive is used in products, the same source code. The same Linux kernel source code is used in products, and build root is used in products live as well. So lots of teaching resources, labs, exercises, and tutorials. Now, just to wrap up the whole workshop, MIPSfpga bridges the gap between toy processors and industry level processors. It's an excellent resource for a wide variety. So many people basically come from different backgrounds. Some of them focus on microcontrollers, some whole VLSI design, some want verification, some want SoC design. So it's an industrial level tool which can be taken at any on any angle in any course. Some courses are more suited to advanced master graduate courses, and some labs are okay for undergrad or upper undergrad. There's a lot of material available on the IUP website and the community forums and everything, as Robert explained. And technical support is not my email address, it's this forum. So some people, I have received questions and then I do redirect them to the community forum. There are other forums on the website as well for just specific MIPS queries, non-MIPS FPGA. If you have some assembly code or something like that, there's other people who can help with that as well. This is a culmination of a lot of hard work by many people. It will take too long for me to say the name, and so that's basically all these guys contributed. And of course, Robert here, Sarah Harris here, Danny here, they contributed the most in terms of building up the whole thing. The rest of the guys we assisted in a little bit.